So, welcome back. What we are going to discuss today is the next non-invasive velocity measurement technique, and the technique name is radioactive particle tracking technique. Now, as the name suggests that we are going to use a radioactive particle and we are going to track the motion of that radioactive particle to get the velocity field. Now, this technique is actually very versatile technique and has been implemented on many multi-phase flow reactors, and the major advantage of this technique is the use of the gamma ray. And unlike PEPT, positron emission particle tracking, here we use actually this gamma ray source itself. It means what it gives the luxury to use a source strength as well as source energy as per the application. So, if suppose I have this column which the column diameter is very small, then I can use a source which can have a very low activity. Now, activity, as I said, has been defined is the disintegration per second. So, number of gamma rays disintegration per second. So, suppose if I am talking about the activity of 1 Curie, it gives 3.7 into 10 to the power 10 disintegration per second. It means it is 3.7 into 10 to the power 10 gamma rays will be emitted per second by the particle. So, I can emit I can choose a source of different energy, I can choose a source of different activity or strength, and therefore, I can use this thing or this technique for any kind of system, whether the system is transparent, it is opaque, it is a smaller diameter, it is a bigger diameter. What you need to do? You need to prepare the tracer particle accordingly, and that we will discuss. So, what we do in this technique, the major advantage, as I said, is the technique is a very versatile technique. It can be used for any system, whether it is a gas solid, it is a gas liquid, any phase fraction, it does not matter that whether the discrete phase fraction is 5%, 10%, 30%, 40%, 50%, any discrete phase fraction we can use this technique. We can use this technique for opaque system because I am using a gamma ray. So, it can penetrate almost anything. I can use it for the gas solid system because what I am doing, I am just preparing a tracer particle which is going to track the motion of the phase of interest. So, let me elaborate about this technique now with the advantages which I have discussed, and I will also discuss the disadvantages at the end of this technique. So, what I said, it is a radioactive particle tracking technique in which I will use a single radioactive particle, and this is very critical that we use a single radioactive particle as a marker of the phase whose velocity I need to map. So, suppose if I have to map a velocity of a solid present in a flow in a say gas solid fluidized bed or liquid solid fluidized bed, I will take the tracer particle, this radioactive tracer particle exactly of the same shape, size and density. So, it means I am choosing one of the identical particle, and making it radioactive by doping some radioactive element, and then after doping that I am keeping the density of the particle, shape of the particle, size of the particle exactly same as of the other particles present. So, my tracer particle is none but one of the billion of the particles or several particles which are present in the column of interest. Now, because these are radioactive particles, what it will be happen in the case of the movement, suppose in the gas solid fluidized bed, so once the solid will move with the other solid, this solid will also move because it has a exactly same property. Now, during its path, what it gamma ray source does, it emits photons or gamma rays, depending on its strength. So, we know that strength, and if I know the strength, I know that this much gamma emission it will do per second. Now, we place some scintillation detectors, and we will discuss about the functioning of the detector later on, but these are the scintillation detectors available which are specialized detectors to absorb this photon counts which is emitted by the source. Now, suppose the particle is here, it will emit the gamma rays, and all the we place detectors around the column of interest, and all the detectors acquires the gamma ray or acquires the photons at the same time. So, it means all the detectors are fired at the same time. So, they are acquiring the gamma rays at the same time. So, what will happen? We prepare a identical particle marker of the phase, and that is why I am saying marker of the phase. In case of the solid, the size, shape and density of this tracer particle will be exactly same as of the solid present in the flow. In case if you want to do the liquid tracking, the particle which you present should be very small in size and the density of the particle should be equal to the density of the fluid. It means you have to prepare a particle which is neutrally buoyant. Now, if the particle is neutrally buoyant, if their size is very less, then what will happen? It will actually follow the path of the fluid if the Stokes number is less than 1. Okay. So, in that case it will just keep on following the path of the fluid and you will track the motion of the fluid. So, this is the technique which gives you the advantage to track the motion of solid, motion of liquid, everything. Now, with the path, once the pressure particle will move inside, suppose in this case whatever I have drawn for the gas liquid and this pressure particle is neutrally buoyant with the liquid, whatever I have shown here, and once it will move, it will emit some gamma rays. Now, those gamma rays will be actually absorbed by the detectors which are being placed around the column of interest all around at all the location to cover your phase of interest and zone of interest. Now, what will happen? Each detector will record a photon count time series history. So, I will just say that it is a count time series history. So, what does it mean? Say each detector, what it will be happen, suppose I will get a graph where the y axis will be count, I am denoting it with the C, x axis will be time, and you will see that how the counts emitted or photon counts, and once I say count, it means photon counts is changing with the time on each detector. So, you will get a photon count time series history for each detectors with the particle movement. Now, I am using single particle, I want a whole velocity field. So, what I need to do? I need to perform the experiment for sufficiently long time, so that the particle covers approximately all the places inside the vessel of interest or column of interest, and not only one time, it should travel several times to the same location, so that I can also get the mean velocity. So, what will happen? We will discuss all those things. So, what will happen? You will get the photon count time series history on all detector with the time. Now, we know that by using Beer-Lambert's law, that I equal to I naught e raised to the power minus mu into L, where mu is the attenuation coefficient of the medium, L is the distance between the source and the detector. So, that will be there. So, what I need, if I have some calibration position I naught values already existing, then what I can do, I can find it out the distance from each detector. So, by using Beer-Lambert's law, it says that the photon counts will be higher on those detectors where the distance is less. It means this L is less. It means if suppose the particle is placed at this location, the photon counts on these detectors will be higher. I will say, even say, let us include these detectors, will be higher compared to these detectors, So, what will happen? I will get that what is the approximate location of the particle depending upon the photon count time series history. And by using the Beer-Lambert's law, and we will discuss the reconstruction algorithm later on, but let us understand in a very simple language. By using Beer-Lambert's law, what I will get? I will get the distance if I know the attenuation distribution, and this is code that if I know the attenuation distribution, then I will know the distance from each of the detectors of this particle. So, what will happen? If I have 4 such lines or 4 such distances, then what will happen? I will get this and I will get that what is the location of the particle. So, ideally what I need the 3 detectors, because each detector will give me a certain distance. They once wherever they will cut, okay, I will know that where is the location of the particle, and because this is changing with the time, I need the 4th detector to cover the time coordinate. So, 3 detector will cover the x, y, z coordinate, and 4th detector will cover the time coordinates. So, I need 4 detector to reconstruct the position of the tracer particle, but what I have right now, I have several detectors. So, each detector is going to give me a distance, that how far this particle is, and by solving all this distance or all this count time series together, I will get the exact location of the tracer particle. And when I am acquiring the photon counts with the time, what I can do, I can find it out how the tracer particle position is changing with the time. It means this I can convert in terms of the position. So, I can get the Lagrangian position time series of the particle, and from there Lagrangian position time series once I have, I can find it out the local velocity of the particle or local velocity of the tracer particle by using just simple delta x by delta t is equal to velocity. So, I am getting position with the time, I will get velocity with the time, or I will say that Lagrangian velocity of the tracer particle, because I am moving with the particle with the time. So, I will have Lagrangian position of the particle, I will have Lagrangian velocity or local velocity of the particle. Now, as I said, we are performing the experiment for sufficiently long time. What will happen? The particle will move each location several times, and then by doing the ensembled average of all those all those times, once the particle comes to a fixed location, we can calculate the mean velocity of that position, and by subtracting the mean velocity to the instantaneous velocity, we can get the fluctuations. And once you have a fluctuation, you can calculate many turbulent quantities like Reynolds stress, RMS, kinetic energy. We will discuss about all those, but you can calculate a lot of turbulent quantities. So, that is the beauty of the technique and the principle of the technique, which is very simple, that we are tracking the motion of a single particle for sufficiently long time. These are the gamma rays particles, so which emits the photons. With what will happen if the particle will move with the time, what will happen? You will get that how the photon count is changing on each detector with the time. From there, if we solve all the detectors photon count time series history simultaneously by using the suitable reconstruction algorithm, then we will get the position of the particle. So, what you will get is the position time series, and from there you can get the velocity. So, this is the basic principle of this technique. The technique looks very simple, but it has many challenges, and we will discuss some of those challenges in this course to understand that what is the benefit, how difficult or how easy it is to implement the technique, how difficult or easy it is to reconstruct the particle position and calculate the post process that data. So, as I said that what we are going to have, we are going to suppose have a system. This is a typical liquid solid system diagram, where these are the scintillation detectors. We call it scintillation detector, which are placed around the column of interest. So, if you see that I have placed the detectors all around the column, and then these detectors are connected actually to a data acquisition system, which records how the photon count time series history will change on each detector with the time. Like suppose these are the 8 detectors I have placed around the vessel of interest. Then these, if you will see, is the photon count time series history for each detectors. So, each graph shows actually the photon count time series history for the 3 detectors. So, if you see, this is for detector number 1, graph is red, 2 green, and 3 it's blue. Similarly, for all the 3 boxes, this is for 4, 5, 6, 7, 8. Okay. So, because I have 8 detectors used in this experiment, I am getting the photon count time series history with for all the 8 detectors. Here x axis is the number of event. If you multiply it with the data acquisition time, you will get that time unit, and y axis is the photon count. Now, you can see that if I track any line, whether the red color or green color, you see that how it is moving. It is increasing, then count is reducing, then again increasing, then reducing, then increasing. It means what? The tracer particle is actually circulating inside the system. Suppose this is the system, this is the detector. Because in the liquid solid fluidized bed, the solids are in batch, then what will happen? The tracer particle will be keep on recirculating. It will be keep on recirculating inside. So, what will happen? Once it will be far, the detector count will be on the detector will be low. Once it will come close, the count on the detector will be increasing. So, that is what we are seeing, that increasing and decreasing count pattern for all the detectors. Okay. So, what we have? Now, we have a photon count time series history of the tracer particle. From there, by using the suitable reconstruction algorithm, I calculate the position of the particle. Now, we will discuss about the reconstruction algorithm. So, suppose this is the initial position of the particle, and it shows that how the particle position is changing with the time. So, how my tracer particle is actually moving with the time. So, this is the photon count time series history, which shows that how the tracer particle is moving with the time. So, what you will get from this data? You will get that how the particle position is changing with the time. I have taken a very small time period so that we can see the trajectory. If you will take for the complete experiment, say for 8 hours, 10 hours or 20 hours, depending upon the diameter of the column or volume of the column, you will see all where this kind of a trajectories. So, what we will get? We will get the Lagrangian position time series history for the tracer particle. From there, as I said, by using delta x by delta t, I can calculate the velocity, and that velocity will be nothing but the Lagrangian time series velocity of the tracer particle or Lagrangian velocity of the tracer particle. So, we will get how the tracer particle velocity is changing. It shows that how sometimes the velocity is higher, sometimes velocity is lower, sometimes velocity is positive, sometimes velocity is negative. As this curve shows that this is positive, this is negative velocity. Why it is like that? Because you are going to see, again I said that the solid is in batch. So, what will happen? It will always remain inside, the liquid is passing through the bottom. So, it will move with the solid liquid up at the center, say, and then it will come down. So, what will happen? Once it will be going up, velocity will be positive. Once it will be coming down, the velocity will be negative. So, we will get a Lagrangian velocity time series, that how with the time Lagrangian velocity of the particle is changing. And then come to the Eulerian velocity or mean velocity or ensembled average mean velocity. So, what we do, like CFD, we discretize the whole column in a small parts, small cells like I did here. So, suppose this is my column. Okay, and suppose this is the diameter of the column. So, whole diameter or whole column we divide in a small grids, say this way, and we see that during the course of the experiment how many times the particle comes in each grid. As I said that we perform the experiment for sufficiently long time, so that I have a sufficient statistics. We wait that for each cell the particle comes several times in each cell. Now, if suppose in each cell, say this cell, if the particle has come say around 100 times, I can calculate the mean velocity of this cell by doing the ensembled average. It means I will do that 1 upon 100 summation I equal to 1 to 100 is Vi. So, I will get that ensembled average velocity of the tracer particle for each location. So, what I will get, I can get, if I plot that, I will get that the mean velocity, and it shows that the tracer particle is moving up near the wall and coming down at the center of the column. So, in this way we can calculate the mean velocity. Once I have a mean velocity, I have the instantaneous velocity, I can calculate the whole fluctuation quantities by calculating the fluctuation velocity. So, we can calculate the Reynolds stress, we can calculate the RMS, we can calculate kinetic energy of the turbulence. In case of the solid phase, we can also calculate the granular temperature and so on. So, all the turbulent quantities you can calculate. Okay. So, this was the flow chart. Though again I said that the system looks very easy or the technique looks very easy, it is not that simple, because RPT is a multi-step process, it is not a simple single stage process. So, what is the stages involved in the RPT? The first stage is the experimental stage. I will not say it a first stage. The one stage is the experimental stage, where we keep the particle free inside the bed of interest and see that how the particle motion is changing with the time, or how the particle position is changing with the time. So, what I will get? I will get that how with the time the count on each detector is going to change, because with the position the count on each detector will change, because some detector, say for particular detector, some position can be close to that detector, some position can be far from that detector. If it is close, your count will be different, if it is far, your count will be different. So, what you will get with the time, how the count on each detector is changing with the time. So, that is what we get from the experiments as I shown in the terms of the graph. Now, I have to reconstruct this thing in terms of the position, as I said to you, by using the suitable reconstruction algorithm. Now, how to do that? To do that, what I need a calibration. I should know that on the same location when the tracer particle was there, under the controlled motion or no motion, how much tracer particle, how much counts was recorded on each detector. Now, this is called calibration step. It means what we are trying to do, we are trying to fix the position of the tracer particle, and we are going to measure the counts recorded on each detectors which are placed around the vessel of interest. Okay. So, that is called calibration step. The calibration step can be done in two ways. One is by experiments, by using the hardware as I said, and physically keeping the particle at several known locations. The way it means what we are going to do, we are going to put the particle at a fixed location, we are going to block the location of the particle, and for that particular location we record that how all the detectors are recording time, recording count for all the detectors are for that position. And then once that is completed, we actually move to the next position and then again calculate that how the photon count will be recorded on each detector for this next tracer particle position. So, that is called experimental way of calibration. However, if suppose you have a bigger column diameter or even a smaller column diameter of a little bit bigger size, what will happen? You have to do the experimental calibration for very large number of points, because you have the particle is moving continuously, you do not have the control that where the particle should go, where the particle should not go. So, it means what? You have to actually do the calibration for entire range, entire column dimensions, which is under the investigation. So, doing the experimental calibration is going to be very tedious and time consuming, and therefore, a software approach has been developed to do the calibration, and that software approach we will discuss later on, but it has been developed to do the calibration, and software also do the same thing. It generates the count recorded on each detector for a fixed position of the tracer particle. So, now what we are doing in the calibration, we make a table, and just like the real experiment, we get a table in which x, y, z is fixed, and the count on the detector on each detector is changing, and that is with the time. So, this is with the time how the tracer particle position and time is changing. Okay. So, that is called calibration, where we change the tracer particle position and we record the count. Okay. In the experiments, what we do? We keep the particle free inside to move, and what we get that how with the time photon count on each detector is changing. So, I have two tables now, one from the experiments, one from the calibration, and this is for the experiment. Now, we compare these two tables, and once I compare these two tables, I will get what? I will get the position of the tracer particle, and that is called reconstruction. So, once I compare these two tables, I will know that how the tracer particle position is changing with the time, and that is called the position reconstruction of the tracer particle. Once you reconstruct the position of the tracer particle, as I said, we discretize the column, we virtually divide the column in a small grid cells like CFD. We see that how many times a particle is visiting each cell, and whatever the time the particle is visiting on each cell, we take the ensembled average of that, and that is called the mean velocity of the tracer particle for that cell. So, that is the way we can calculate the mean velocity, and from there we can calculate the fluctuation and other turbulent quantities. So, this is the steps in the RPT which is being used to process the data. Now, like other technique PIV, LDA or PEPT, RPT is not an off the shelf technique. It means you cannot just not a plug and play device, and you have to fabricate it or you have to install it from the basic nuclear spectroscopy hardware. So, you will get the individual hardware, but you will not get a unit name as a radioactive particle tracking technique. That is one of the major problem with the technique, that there is no ready-made packages available, and one who wants to work with this technique have to understand the basic sciences. He has to understand how to assemble the nuclear spectroscopy hardware and how to use that hardware for the reconstruction, data reconstruction. So, some of that hardware we are going to discuss. So, basically this is the flow chart of the RPT, as I have already discussed before going to the hardware, that how we do that. What we do, we first do the detector calibration, we do the experiment, we compare these two, we get the instantaneous position of the tracer particle, we discretize the whole column virtually in like a grid in a small Eulerian cells. We note down that in each Eulerian cell how many this time the particle comes during all the experiments. So, we get that how the particle position is of this, the number of particle times the particle kind of visited the cell. Then we do the ensembled average. Suppose it is visited n number time, I will just add those n number times the particle velocity divided by the total number of times the particle comes in that unit cell. So, I will get that what is the ensembled average velocity of the particle. Once we know that ensembled average velocity of the particle, what we can do, we can subtract the mean minus instantaneous, I will get the fluctuation velocity. Now, the beauty of this technique, as I said, and if you try to understand, is that suppose if any grid cell if I am talking about, and I said that the particle actually visit the cell several times, say n times, the way it has been shown. So, what does it mean? That you are going to have not only a single mean velocity for each cell, you are going to have not only the Vz mean, you are going to have Vz say fluctuation, and you are also going to have the value that this Vz fluctuation, you are going to have Vz mean value, but you are also going to have the PDF of the instantaneous velocity, say PDF of instantaneous velocity and PDF of fluctuation. Fluctuation velocity. And these two are the major advantage of this technique. So, what I am saying that I am not going to just tell you that what is the velocity or mean velocity at a particular location inside the column of interest. I am also going to tell that what is the velocity distribution for whole experiment, for whole time, for 8 to 10 hours, 20 hours, how much velocity distribution you got for each location. You can find each location, and then you can similarly use that velocity distribution, local velocity distribution. If you subtract it from the mean velocity, what you are going to get? You are going to get that the PDF of the fluctuation velocity. So, what I am going to get? I am going to get the PDF of instantaneous, PDF of the fluctuation velocity. It means you will not only get the mean, you will get that what is the distribution of the velocity at a particular location, what is the distribution of the fluctuation at a particular location. And now, if you are designing the system, you can design your system not based on the mean velocity only, which is the traditional way of doing the designing. We can also consider the distribution in the velocity for each location, and that distribution in the each velocity will gives lot of flexibility to even do the post process the data for all higher order moments, which we will discuss. So, that is the flow chart of the RPT. This is the formula which is being used to calculate the velocities. Like if I say the instantaneous velocity, it is Vz is nothing but delta z upon delta t. Similarly, we can calculate the Vr and V theta, but you need to do certain trigonometry. We will discuss some of that. I will show you the formula that how to calculate Vr, V theta. If you are solving in a polar coordinate, if you are solving in a rectangular coordinate, then Vx, Vy, Vz all will be defined by delta z by delta t. You can calculate the ensembled average velocity, as I already said that in each cell, suppose the particle comes for 100 times, you add all those 100 velocities divided by the number of times particle comes, it means 100, you will get the ensembled average velocity. You can calculate the fluctuation velocity mean minus instantaneous within that cell for all the time the particle comes in that cell. You will get that what is the fluctuation velocity each time, or you can say that you will get that the PDF of the fluctuation velocity in that cell. Then you can calculate the RMS velocity of that cell, root mean square velocity, by using this formula, which is nothing but b prime square. So, if suppose I want that b prime square for this, so I will get, say, if I want the z directional RMS velocity for each cell, whenever the particle comes, there is a fluctuation velocity, I will square them and I will add them, I will get that what is RMS velocity of the particle at that cell. Similarly, I can calculate the Reynolds stress. Reynolds stress is nothing but rho v v prime. Reynolds stress is rho v v prime. So, I can calculate all the 9 component of the Reynolds stress. Suppose if I am talking about this polar coordinate, I can calculate Vr Vz, rho Vr Vr, rho Vr Vz prime Vz prime, rho theta prime, and so on. I can calculate all the 9 components of the Reynolds stress, and we can also calculate the kinetic energy of fluctuations per unit volume, okay, or fluctuating kinetic energy of this per unit volume. And fluctuating kinetic energy has been defined for each cell. Suppose if the particle is coming 100 times in each cell, okay, what will happen? You will see the 100 instantaneous velocity, you will get the mean velocity, you subtract it, you will get the PDF of the this fluctuation velocities. Now, each velocity, say Vr, V theta, Vz, you will get the PDF for Vz prime, you will get the PDF for Vr prime, you will get the PDF for V theta prime. So, you will get the PDF of fluctuation velocity for all the 3 velocity components, and then we can do that averaging, and half rho Vx prime square plus V theta prime square plus Vz prime square, or you can write say Vx or Vr, it will be the nothing but the turbulent kinetic energy per unit volume of the tracer particle. Why per unit volume? Because instead of mass I am taking rho, because in case of the fluid we know the rho, but knowing the mass is many times is very difficult. So, that is the fluctuating kinetic energy per unit volume. We use this formula to calculate the quantities. We can also calculate diffusivity, we can also calculate autocorrelation and all other data. We will discuss that later. Now, as I said, RPT is not an off the shelf technique and you have to assemble it from the basic nuclear spectroscopy hardware. So, let us discuss that what are the hardware which is required for the RPT experiments. Now, as I said that the most typical part of the RPT experiment is the tracer particle, okay, which we are using as a marker of the phase. So, the first hardware I will say is nothing but the radioactive particle, which should be the gamma ray source, okay. And the particle size, if you are tracking, again I am repeating, if you are tracking the solid phase, size, shape and density of the tracer particle should be exactly identical to the size, shape and density of the other particles which are present in the flow. In case of liquid tracking, the particle size should be smaller and the density should be equal to the density of the liquid. In case of the gas tracking, I am sorry, that is the major disadvantage of this technique. You cannot track the gas by using the RPT technique. Why? Because it is very difficult to find a tracer particle, solid tracer particle, which can match the density of any gas, and therefore, the gas tracking cannot be done. It can do either the liquid tracking or the solid tracking. So, the first hardware is your radioactive source. This is some typical photograph of the radioactive source, and you can see that depending upon the application, the size, shape and density of the sources keep on changing. Okay. So, these are the typical sources which we use in our laboratory, and that is what I have shown, that it can be from very small to very big, and the type, shape and density of these particles are kept exactly same to the solid present in the flow. Okay. The second hardware and is scintillation detectors, which job is to actually record the photon counts which is emitted by the tracer particle. The third is to multi-input data acquisition system, we also called it MIDAS, its job is to use the or kind of acquire the data recorded or transferred from the detector. So, detector will absorb the count, it will transfer that absorbed counts to the MIDAS or to the electronics, and electronics job is to count that number of incidence of the gamma ray which has been detected by the scintillation detectors. So, that is the job of the MIDAS, and then finally, you require a PC for the data acquisition as well as data processing. So, these are the typical hardware. Actually, this is the three main hardware which you require for the RPT experiments. Okay. This is a typical diagram of the scintillation detectors, and we will discuss this diagram in later in more detail. So, this is a typical diagram of a scintillation detectors which we use it, and if you see that the scintillation detector is divided in two parts. The first part is called crystal, and this part is called photomultiplier tube. So, this part is called photomultiplier tube. Okay. So, the detector is being actually made of two parts. First part is the crystal which actually do the absorption job. Another part is the photomultiplier tube, which is used generally for this supplying the this voltage as well as to count the signal which is being generated during the absorption of the photon counts. So, how the scintillation detectors work? To see that, let us assume this is my scintillation detectors, these are my photomultiplier tube, and it is connected with a counter. Now, let us forget that what kind of counter it is, but let us assume that it is a counter which counts the signal. So, what will happen? Once a gamma ray is actually emitted on the crystal, what will happen? The crystal will actually absorb that gamma ray. Okay. Now, once the crystal will absorb that gamma ray, okay. So, suppose this is the time when the particle has incidented on the detectors, it will emit a photoelectron. So, what will happen? We know that once the gamma ray is absorbed in any material or any crystal, what happens? That the crystal electrons goes to excited states because they got certain energy. Once they will come back from that excited state energy, they actually emits a photon, a photoelectron, or so that photoelectron actually is covered to the photocathode to generate an electron, and that electron pass through this photomultiplier tube, which has actually several diodes placed to enhance the signal. It actually passed through that, and once it passed through that, it reached to the anode. Once it reaches to the anode, like this way it passes, it generates a pulse, a current signal, and that pulse or current signal is being actually counted by a counter which is being placed after the detectors. So, each photon counts, or each photon which is incidented on the detector, adsorbed by the detectors, because only once the photon adsorb, it will emit a photoelectron, it will go to higher energy state, and then it will emit to photoelectron. So, so for each gamma ray which has been adsorbed by the detector, each current pulse has been generated. So, it means if you just count the number of times the current pulse has been generated between the data acquisition system. So, say if I am acquiring with 1 second data acquisition frequency, after every 1 second I am acquiring the data. So, I will see that how many times this current pulse has been generated within that 1 second, and that is been called, or that will be shown as the photon counts on that detector for that time period, for that delta t. Okay, and you will get this kind of, whatever we were discussing, you will get this kind of a map for each detector, that how the photon count is changing on each detector with the time. Clear? So, now if the detector is closed, definitely number of intensity will be higher, more number of photon counts will be incidented. If detector is very far, the cone angle, the view angle, the factor, the attenuation will be higher. So, the number of photon counts emitted or incidented on the detector will be low, and that is why the counts on that detector will be low. So, that is the basic principle we use, and we get the photon count time series history. Okay. So, this is the way the scintillation detectors work, and there is a crystal inside. Most of the time there are different type of crystal available in the market for different type of detectors, but most of the time we use NaITL, it means sodium iodide doped with thallium is used as a scintillation detectors. So, these are sodium iodide detectors. Why it is being used? Because it is very cheap compared to the other detectors like BGO or any other detectors. This is very cheap, and that is why for RPT application generally we use sodium iodide detectors, scintillation detectors, which is doped with the thallium. Okay. Now, the second hardware which is important is whatever is being put, which I keep on telling till now, is a counter which is being placed after the detectors. So, there are several advancement is there in the RPT hardware. Okay. So, earlier this system used to be very huge, but with the modern development of the electronics or development of modern electronics, now the system size has been reduced. So, what we need actually, these detectors, as I said, have a photodiodes, and those also need a energy. So, what you require? We require certain high voltage to maintain the particular potential within the that detectors. Okay. So, you need a high voltage supply. Then the current pulse which is being generated by incidenting one photon count or one gamma rays or photon on the detector, the intensity of that signal is very weak, intensity of that current pulse is very weak. So, what we do? We need an amplifier or series of amplifier depending upon the intensity. We can have a pre-amplifier, we can have an amplifier which will actually amplify the signal, so that I can see the signal and I can discriminate the signal from the noise. Okay. So, I will get that amplifier. Then we use a single channel analyzer or multi-channel analyzer. Now, what that the job is, as I said, that single channel, it means it has a single channel which records or which counts the number of photons incidented on each detectors. Okay. So, this is nothing but a counter, but it is also a single channel analyzer. So, it is also analyzed that the photon which has been incidented was of what energy, because if the energy of the photons was very high, then the probability of adsorption of those photons on the scintillation detector crystal is low, and so the intensity will also be different. So, we calculate that energy of the system or roughly energy of the system, and we get that this kind of a photo peak curve. So, if you see that for each detector, each time you will get this kind of a curve for each detectors. Okay. Now, this is called photo peak. We will discuss about the photo peak once we will do the tomography things, but what we get is actually you get that how the count energy is changing. Okay. Number of photon counts versus number of photon count energy. So, you will see that this kind of a curve, and then in this channel we put some discriminator of filters to record the count only which is coming directly from the source, and those counts or those area is called photo peak. Okay. So, what will happen now? There is a question, there is lot of things to discuss. I am trying to cover in a little bit brief. If you have any problem, please discuss me over the assignments. You can drop me the questions. I would love to answer those things. So, what we do actually, that even our tube lights, okay, is also emitting photons. Now, hardware is not able to detect the difference between that photon and the photon which is coming from the gamma rays, other than the energy, that the energy of these tube light photons will be much lower compared to the photons which is coming from the gamma rays. So, and there will be some noise also, as you know that all the electronics generate some noise, and that is why we put the pre-amplifier and amplifier, so that I can increase the signal to noise ratio. I can amplify my signal so that I can reduce the noise. Now, this is the way. So, all these things are incidenting, they are actually contributing towards the count. So, to detect that which are the count which is coming from my source, which is relevant to me, what are the counts which are not coming from my source or which is coming from the source, but has been got attenuated because of the several collision, it means which is not directly coming or straight coming from the source, we have to neglect those counts. Okay. So, we draw a number of photon on y axis and energy on the x axis, and you will get this kind of a curve. In that curve you will get a prominent peak, and that peak will actually represent the energy of this source. So, like in this case we are using cesium 137 as a source, which energy is 662 keV, and that is why we are getting a peak at 662 keV, and this is the sample where the red bracket you are seeing is called the photo peak. It means that is the peak, or that is the peak which is directly coming from the source. We are very sure about it. So, we put a discriminator or filter which actually remove the counts which are below than this photo peak, or below the energy which is below than this photo peak. It means any energy which is less than this, it will be discriminated, it will not be kind of recorded. Any energy which is higher than this, which also not be recorded. So, we record only the photo peak counts, and that is what we call it as a photon count time series history, and that is being done by the single channel analyzer or multi-channel analyzer, where we can have multiple channels or energy channels. Okay. So, this is the electronics part of it, how the data has been recorded. So, the photon count which we record, actually the time series history, the graph which I have shown you, is only for the photo peak, it is not for these counts which are actually noise. Okay. So, we record the photo peak counts. Now, with the development of the electronics, earlier we used to use all these electronics separately, and that is why the system used to look very bulky. But now with the development in the electronics and coming with the modern electronics nowadays, we actually can accommodate all these devices in a single device, and that is called multi-input data acquisition system, or MIDAS, and this is the multi-input data acquisition system. And this one unit, if you will see, this one unit is called single channel analyzer. Now, these knobs you are seeing, that knobs are actually to set the setting of the detectors. So, one knob is for high voltage supply, that how much voltage you want to supply. One knob is for the discrimination, putting the limits on this energy spectra, so that you can acquire the count only those counts which are directly coming from the source. So, this is another device we need to do the recording. Now, there are several steps, as I said, in the RPT. In the RPT, there are several steps, as I said, that first step is the photon counts, second step is calibration, and third step is reconstruction. So, what we were discussing about the photon count till now, and the hardware which is needed for the photon count experiments. Now, as I said that for the reconstruction, what you need to put the tracer particle at a various known location before performing the experiments, and the challenge is to do that at in situ condition. In situ condition means, suppose I want to perform the experiment for a particular solid circulation rate or particular amount of the solids, say in the gas solid system, particular gas velocity, I have to do the experiments calibration for exactly same condition. It means for that much amount of the solids and for that solid velocity, for gas velocity. So you have to do that, the calibration at in situ, and during that in situ calibration, now we put the tracer particle at several known location and record the count on the detectors. Now how we can put the tracer particle? There are several ways to put the tracer particle, and if you go and see the literature on the radioactive particle tracking, you will see that everyone devise or derive a quantity or design a calibration device based on their column operating condition, column geometry and column size. So what we are going to discuss is one of the method which is very simple, and we always use that in our laboratories. So now the first question is, you can ask that why in situ calibration? Because I said that if we are using I equal to I naught e raised to power minus mu L, what I need this attenuation coefficient for that location of the tracer particle, and this attenuation coefficient will be differ based on the operating condition. So suppose if I am operating a gas solid fluidized bed, say this is my solid and this is the packed bed condition suppose, and we know that if I pass the gas, a velocity will come when the particle will start moving. So in the packed bed condition, if suppose this is my tracer particle, the red color, and these are the detector placed, what will happen? The attenuation will be more because all the solids are perfectly packed. So attenuation, it will see lot of solids. Now definitely depending on the density, say gas have a very low attenuation, the material which have a higher density is going to have a very high attenuation. So you are going to see lot of solids, your attenuation will be different. So what will happen? You will see the different count on all these detectors. Now if I fluidize, suppose, what will happen? Similarly, these are the detectors which will be placed, say, and now the particles has been fluidized. So what will happen? If they will fluidize, the particles will move far from each other. And now if suppose this is my tracer particle, now the counts recorded on these detectors will be different because now it is seeing less number of the solids. So because it is seeing less number of the solids, it is going to have less attenuation. So now the count will improve. So that's the reason that you need to have, you have to take care of this mu distribution, which is clearly the function of the operating condition, and that's why we need to do the calibration at in situ condition. So what we need to do at in situ condition, at the same operating condition, we need to put the tracer particle at several known location. Now there are several ways, as I said, in literature everyone use a different method depending upon the operating conditions. Say what is my operating condition, whether I am operating at a very high pressure or very high temperature, whether it's a gas solid flow, whether it's a liquid solid flow. So depending upon the type of the reactor, depending upon the size of the reactor, different calibration strategies has been developed by the different researcher, but idea is to place the particle at a known location. So generally what we do in our lab, we put the ports, several ports near at the wall. So these are the ports, okay, and I know the ports because while designing the column I put the ports, I know the R, theta and Z position of these ports, okay. So I can say that instead of R, theta and Z, say if it's a rectangular, I will say X, Y, Z position of the tracer particle. So I already know, of these ports. So I know this ports. Now we take a rod and we put a tracer particle on the top. I don't know how much it is visible, but I will show the next figure where you can see clearly that there is a tracer particle which is on the top. So you can see that there is a small tracer particle here which is on the top. Okay, so this is the tracer particle. And we put it on the threaded rod so that you can move the thread and you can change the location of the R value. So the Z of the port is fixed. Okay, the theta of this port is fixed, and you are now changing the R value. So you will change the R, theta and Z position of the tracer particle, and you will record the counts. Okay, so that is the one way of doing the calibration, but that should be at in situ condition. I have taken the photograph at empty column so that we can explain the facts. So what we do, suppose this is the opaque column. So we take this kind of a threaded rod. If you see this figure, we put the tracer particle on the top. This is my tracer particle. And at the in situ condition, we place the tracer particle through these ports, okay, and they are detector placed which actually record the counts. Now definitely these detectors are going to record very high counts compared to the other detectors which are placed here. So I will get for the calibration, if I put it here, I will get that what is the count recorded on each detector for this location of the tracer particle. It means I will have say r theta z, and I will have C1, C2, C3 and so on all detector how the counts is changing for r theta and z. Okay. Then what I will do, I will just move this thread further, so the particle will move further inside. So I will change the, it means what I did, I changed the position of the r. Again I will record the count on each detector. So what will happen, I will have a lookup table, we call it lookup table, which says that how the particle position, how the detectors counts are changing with the particle position. Okay. So this is called calibration. Then we perform the experiments, we get the time versus count, we compare both two and we calculate that what is the position of the tracer particle. Okay. So what you will get actually, if you do the calibration experimentally, you will get it that how the count is changing with the distance from the tracer particle. So I know the position of the detector. Okay. I know the position of the detector. It means I know the x, y, z coordinate of the detector. I know the x, say I will write it as a detector. I know x, y, z position of the particle, I know these coordinates, I can calculate the distance, okay. That will be nothing but under root x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. So I will allot 1 to this, say 2 to this, I will get that distance. So what I will get, how with the distance tracer particle position, you can say distance from the detector, a particular detector, the counts on that detector is changing, and as we know it is going to follow I equal to I naught is from minus mu L. You can do the calibration, you can validate it whether it is following or not, and you can see that it is following that curve, a bell kind of a curve or a Gaussian curve, which is showing that it is following the Beer-Lambert's law. Okay. So it is the exponentially the counts recorded on the detector is changing with the distance. Okay. So similar graph you can prepare for all the detectors. So you will know that at what distance what count you are expecting on that detector. Okay. Now why we need several detectors? Because there can be a position when suppose one can get confused and one can ask the question, suppose this is my column, I am using this two detector. If suppose the particle is moving vertically downward, then the count on this location, distance of this location and this location will be the same. So what will happen in that case? In that case, I will not have a unique picture. I can either reconstruct this position of the particle or this position of the particle, because if I will go to this lookup table, they will give me the same count, say this count. If I am distance of say 500, this is going to give me the same count. And that is the reason why we place the several detectors to cover the entire area. So yes, it's true that if you will calculate with one detector, you will not get the unique solution. So if I take the counts, and that is the reason that why while reconstructing, we take the count from all the detectors. Now if suppose I have two detectors here, what will happen? For this location, now these distance are low, these detector distance are low. So they are going to get high counts. They are going for this location, they are going to get low counts, and the vice versa will be true for this location. These two detectors will get higher count and these two detectors will get lower count. So if I do the combined, if I take the effect of all the counts, all the detector counts to reconstruct the position of the particle, I will always get a unique solution, and that is the major plus point of the RPT technique, that you always get a unique solution because you have only one particle where the counts are coming, compared to the other technique where the unique solution is also sometimes difficult. Okay. And that is the major added advantage of this technique. So what we do? We generate the photon count time series history, that how the photon count time series is changing with the tracer particle location. Okay. So distance and location is same, you are moving far, distance is increasing, you are coming close, distance is reducing. But as I said, it is impossible to do the calibration, experimental calibration for all the location inside the tracer particle, inside the reactor or inside the column of interest. Why? Because of the two position, it is very difficult to put up ports at all the physical location, because the ports require some physical area. So, you cannot put the tracer particle at all the location. Second, it will be very time consuming. For each time, what you need to do it in situ condition, you have to put the particle at several location, pull the particle out. Now, if you are pulling the particle out, suppose it's a gas solid or liquid solid, what you need to do, you have to first shut down the system. Neither the solids will start leaking from this ports or liquid will start leaking from this ports. So, what you need to do, you have to shut down the system, then you have to remove it, then again you have to put it into the other port, you have to close this port, you have to put it in the other ports, you have to again operate the system, you have to wait for a steady state to achieve, and then you have to do the same exercise, that you change the location. So, there is two major disadvantages of the experimental calibration. The first is, it is almost impossible to do the calibration at all the location inside, and remember that the tracer particle is free to move anywhere inside. So, what you have to do? You have to actually need the calibration at all the known location, or you need to depend on the interpolation. Now, we know that the interpolation had certain accuracy, we do not want to get involved in that. So, for the better accuracy, we want that I should have a calibration count for all the possible position inside the vessel of interest. Okay? So, for that purpose, as I said earlier, that the calibration we cannot do only, we cannot depend only on the experimental, we have to also do a software calibration which is actually based on the Monte Carlo algorithm. Now, how to do that, the software calibration, we will discuss it later. Thank you.